So multiple integrals. So in here, we'll just have the process of evaluating a multiple integral. And let's look into the specific learning objectives for this last module. So in here, you are expected to be able to evaluate double integrals, triple integrals, and discuss the properties of integrals that is also applicable to this particular multiple integrals. So before we do the evaluation, we'll first discuss the properties that you can apply, and properties of integration, that is. So you can see here, you can see you have two double integrals. The D here that you see written below the two integral symbol represents the region in which we're interested in the area of. So you can see here dA. We are determining the area of a particular region D if you are determining or evaluating rather a double integral. So the double integral is used to integrate over a two-dimensional region. And what do we determine for this two-dimensional region? Its area. Now, let's say we have this particular region. So it's a plane region bounded by this red curve and this blue curve, and bounded by these lines, two vertical lines A and B. Now, if we intend to determine the area shaded here in green, and we need to apply the process of double integration, we need to change the differential of A here into specific differentials in terms of X and Y. If we do that, our specific double integral could be written now in this manner. By the way, class, the double integral and the triple integral that will be given you is already given as is. So meaning you'll not be the one who's going to write the expression for such an integral. Meaning what you will just be simply required is to evaluate. So let's say you're given this particular double integral. How will you evaluate? We start evaluating our double integral or even our triple integral by integrating in terms of the first differential. So whatever is the first differential, you look for the variable that appears on it. That dictates what particular variable will be integrated in this function of x and y. Now you may wonder, how come, Miss Ali, that your function is a function of x and y? It's because, class, you have two expressions in here. And it could be that the resulting function here for these two curves, which represent the boundary of this particular green shaded region, is having both the variables x and y. So in the case of evaluating a single integral, there's a need for you to express one variable in terms of another. That way, it would be possible for you to determine the integral. Now, in the case of the double integral, if your function has more than one variable, it's okay. Even if it has three variables, it's okay, as long as the variable that appears here in your differentials, you know. Like this, for example, this is y. So meaning, you will integrate this function in terms of y. And the next question is, what about the other variables, Miss Ali? Let's say, for example, I have x and z added to the variable y. The rest of the variables that appear in your function will all be considered as constants if you are integrating with respect to just one variable. Actually, you're just simply integrating with respect to one variable. So if you're integrating in terms of x, other variables that appear here in your function of x and y, specifically in that case, that would be the x variable, they will be considered as constants. So you will only integrate the y variable. But that is just the first part of the process, because after integrating with respect to y, considering x as a constant, you need to substitute the limit here. Whatever are your limit, for the lower limit and the upper limit, you need to substitute it on your answer, just like the way you do it when you're dealing with single integrals to evaluate. When you're done substituting the limits here, of course, you substitute first the upper limit minus the expression lower limit. Where do you substitute it? You substitute it only to the y variable because you have only integrated with respect to y. You have considered x as a constant. When you're done substituting and simplifying, it's important that you simplify, you go to the next differential. So when we evaluate, we start from the inner part going out. So this would be the first differential. The second differential will be your next. And you will this time integrate with respect to x. So your simplified answer here will be integrated in terms of x. If there are y expressions that appear in your simplified answer here, you will consider those y variables as constants. Okay? So you have evaluated with respect to x for the second time, considering y as constants. After that, you substitute this lower and upper limit. And that's it. You already evaluated your double integral, which represents the area of this green shaded region, bounded by the curves g sub 2 of x and g sub 1 of x. Okay? And in here, you have A and B. Actually, if I may just discuss it in here, since you started class with dy, so meaning you will have this, you have this one. It's as if you have this dy, the g sub 2 of x and the g sub 1 of x appears as your upper and lower boundaries. Why? Because this shaded region in terms of y vertically is bounded. Vertically is bounded by this curve, which is g sub 2 of x, and this curve, which is g sub 1 of x. You put g sub 1 of x in the lower limit because it's the end part here, the lowest portion of the bounded region. You put g sub 2 of x because it's the highest upper portion of the curve. Okay? Now, that is in terms of x. Now, what about in terms of, in terms of y? So, this is how your area is bounded by vertically. So, upper part is g sub 2, this red curve. Lower part is g sub 1, the blue curve. What about horizontally? So, this time, you will have dx. So, what is the boundary? Anong pinakalayo ng x? Ano ang pinakalapit na x in terms of this vertical axis y? So you have the farthest is b. So you see it's as the upper limit, and the nearest to the y-axis is the lower limit. Do you see? We determine the area of this region by integrating with respect to y. So our limits will be our curve themselves, the representation of the equation of the curve with respect to x, your y with respect to x, and then in terms of x, it's bounded from a, x value a to x value b. But nonetheless, class, you won't be required to set this up on your own. I'm just telling you how it's done in terms of the application. Purely, you will just need to evaluate multiple integrals in here. Okay? But if you intend to learn more, of course, there's no limit in what you can learn. You can always do your own independent study. Now, we proceed to the next slide here. Now, we have this region. Again, the area of this region. And you have the function of x and y here. So this time, we start with dx. We start with the x variable. And what is the x? So this is your curve. Sorry, class. I will just have this annotated. So in terms of x, this is the farthest x. And this is the nearest x to the vertical axis y. So what happens is, so this is your function of x and y. And what happens is your limit will be starting from h sub 1y to h sub 2y. So your limits here, after you have done evaluating this particular function with respect to x, considering y as a constant, now is in terms of y. So your answer here for the limits or the values not values. The expression that appears here in your limit will have y as the variable. Because you have this as the farthest here for the x, and this is the nearest with respect to x. Now, what about y? So if you could see what's the lowest and the highest point in here. Your lowest point is C, your highest point is D, vertically. So you can see here, C to D. The procedure is still the same as how I have explained it to you a while ago. Okay? Now, you also applied the same principle with triple integral. So these are the properties of the double integrals, which is also applicable for triple integrals. If you have several functions, what you can do is evaluate the integral, the double integral of such functions separately. You can do it piece by piece. Evaluate first the function of x and y, dx, dy, then add to that the g of x and y, dx, dy as well. This is the same as if you are dealing with single integral only. Now, if you have a constant, you place the constant before the integral symbol. Process the integral, then your answer, your final answer, or the final expression representing the answer will be multiplied by c because it's a constant. If the region D can be split into two separate regions, D sub 1 and D sub 2, then the integral can be written as. So for example, you have a composite region, meaning the shape could be a combination, for example, of a semicircle and a rectangle. Let's say, for example, your shaded region is a combination of a rectangle and a semicircle. So you can divide that into two regions, one for the rectangle and one for the semicircle. Determine the area of the circle, determine the area of the rectangle, whichever of these two represents such, and then just add your answers. I'm talking about now the specific application of the double integral in terms of two-dimensional spaces wherein you are to determine the area of. Okay? You can apply such also to triple integral. So I have one here specific example. A double integral of e raised to x over y dx dy. The first integral having limits y to y cubed. The second having limits 1 to 2. So what's done here? Okay, let me annotate. For your function here, this one, you will evaluate in terms of x. So meaning y is a constant. In this case, you will have e raised to, I can place the 1 over y before the x, meaning I consider this as a constant. So if I will integrate with respect to x, I need to have the derivative of the u in here, which is 1 over y, right? 1 over y dx. In that case, I don't have the 1 over y, so I introduce the 1 over y here, and I place the y here. Y over y is 1. So that's the reason why you have this as the answer. Y e raised to x over y, because that's your e raised to u expression, and you have the limits here, y and y cubed. Now, if you substitute, so you have y e raised to x over y, and you will have here y and y cubed as the limits. Your limits will only be substituted to what variable? Your limits should only be substituted to the variable x because you have integrated with respect to x. So, diri ka ma-substitute sang sininduha. So, if I will continue here, I'll just place it in here. So, you have y. You need to substitute the upper limit first, e raised to y cubed for the x over y. That would be y squared. Minus lower limit is y. So, y over y, that would be 1. So, e. This is the answer now. Y e raised to y squared minus e. Distributed the y already. Then you do your next integration. You will integrate with respect to y. And then substitute the limits 1, 2. So if you evaluate this one, the derivative of your y squared is 2y dy. So you place 2 here, and you place 1/2 outside for the first integral. So that is why you have 1/2 e raised to y squared. For this one class, this e raised to 1 is just a constant, so you just need power rule for the y. That's y squared over 2, then e. And substitute 1 to 2 to your y's, the y's that appear in your expression. So 1/2 e raised to y squared, 2 squared, that would be 4, minus, so this is y squared, so that would be 2, okay, 2 over 2. Wait, where is it? 2 squared, that would be 4 over 2, so that would be 2. E raised to 1. Now, when you substitute the lower limit, you may think that this is lacking something. So this is your upper limit minus, so your lower limit would be 1/2 e raised to 1 minus 1/2. This is also 1 e raised to 1. So the whole thing cancels each other, which is 0. What I'm writing here is for the lower limit substitution. What is written here is the upper limit substitution, only because anyway this one is 0. Okay? Any question? So you consider the other variables as constant when you are evaluating in terms of a particular variable. And before you do the next integration, you substitute first the limits. Okay, I'll clear my markings here. And we'll go to the next. This is another one. You have 4xy minus y cubed dA. Specifically, the dA is dy dx. So dy dx, so vertically, it's bounded by the square root of x here. The equation of the upper curve is square root of x, the lower curve is x cubed. You will evaluate first in terms of y, so you consider x as constant. X as constant, so this is 4xy squared over 2, so it became 2xy squared. This one does not have the x, so you just do power rule. Then substitute the limits to y. So you substitute square root of x for this y squared here. So that would be x times x, so that would be x squared. Okay? And for this one, square root of x for this one also, that would be just simply x squared. Then you have the lower limit to substitute in here again. Remember, you will substitute only to the y. Now, if you simplify your answer, this will be the final answer for that. Then you integrate this with respect to x, which is very easy because that would simply be power rule. So power rule, substitute the limit 0 to 1, limit 0 to 1, and your answer will be 55 over 156. You get it? Or other way of writing the boundaries here, vertical and horizontal boundaries, is this. On the x, this green region is from 0 to 1. So x is greater than 0 but less than 1. Okay, this region. For the y, vertically, your y is from x cubed, y greater than x cubed but less than square root of x. The way it's written here as to what bounds or what is the interval for x and y helps you in writing the correct limits here. But you won't do that anymore because, as I've said, you will be provided with the expression to evaluate. Okay? Now, in here, you have r dr d theta. You will integrate first in terms of r, so that's r squared over 2. These are your two limits, 2 and 4 sine theta. If you substitute these two to the r, this will be your expression. Then evaluate with respect to theta, and then substitute the limits. So the expression actually, or the area in here, is this pink area. Okay, so find the area outside the circle R equal to 2, but inside R equal to 4 sine theta. So this is your circle which has radius 2, and this is your circle which has radius 4 sine theta. So it's inside this R equal to 4 sine theta circle, but outside the R equal to 2 circle. So this is the pink region that you are to determine. Okay? Now, for triple integrals, it would look something like this. How do you process it? Exactly the same as the double integral. You work your way from the innermost differential outwards. Okay, consider the variables, the other variables constant except the variable that appears in your differential. As to the application of the triple integral, it's used in determining volumes of three-dimensional spaces or regions. So, di kay volume na siya, kundi three-dimensional na siya. Sa mo na iya nga application sa triple integral. And you have here an example. A very simple example on the triple integral evaluation of 8xyz dz dx dy. So first you will consider integrating with respect to z. So it would be 8xyz squared over 2. So it becomes 4. Substitute the limit to the z. So you will have only 4xy dx dy. Now integrate with respect to x. So that would be 2x squared y. Limits 2 to 3. You substitute for the x. So if you substitute for the x in here, sorry. If you substitute for the x in here, you will have substitution. You have 3 squared y minus 2 times 2 squared y. So this would be 9 times 2, 18 y minus 4, 8y. So that would be 10y. So 18y minus 8y, that would be 10y. The last integration is in terms of y, so that would be, so this would be 5y squared from 1 to 2. So 5 times 2 squared minus 5 times 1 squared. So 20 minus 5, so that would be 50. Okay, 15. That's it. And then let's say if I have here this one, very simple, even simpler than the previous because there's no function that appears. You're just simply going to evaluate starting with z, y, and x. So what's the answer for the first integral? Of course, your first integral will have an answer z for the dz. And you substitute 0 to 3, 0 to 3. So this would be 3 dy dx. In terms of y, that would be 3y, limits is 0 to 2. So you will have 6 dx. So that would be 6x times 1. That would be 6. Okay? So it's easy as long as you know how to integrate. No, nothing to critically think about because you're not going to translate a worded problem into an integral expression. You're not going to mathematically model a particular condition using integral calculus. Or we can have the region here, this three-dimensional region volume, still dz dy dx. So z 0 to 5x over 2. So you will have 5x over 2. Integrating with respect to y would be 5xy over 2. These are your limits. You will substitute it to y. So you will have this one, if it's 3, that would be 15x over 2. For this one, that would be 3 15x squared over 2. Over 2, that would be 15x squared over 4. The last integration is with respect to x. So 15x squared over 4, you have 15x cubed over 12. 3 times 4, 12. Then substitute 0 and 2 for your excess, upper and lower limits. And this will be your answer. Okay, just do it the way you evaluate single integrals. In here, the only catch in here is that you don't forget that you will substitute the limits on the variable that you have integrated and simplify before you do the succeeding integration. Okay, for this one, you have x squared yz, x squared yz dx dz dy. If it's in terms of x, so you will have x cubed over 3yz. If you substitute the limits, negative 2 to 1, you will have 3yz dz dy. If you integrate in terms of z, you will have 3yz squared over 2. Substituting limits 1 to 5 gives you 36y dy. Integrating this, that would be 18y squared because it's 36y squared over 2. So 18y squared, substitute the 3 and the 0 for the y squared. So you have 9 and 0. So the volume of this box, this three-dimensional figure here, is 162, based on this representation. Okay, you have any questions? This ends our integral calculus class.